Welcome class to our first lesson on scientific notation. We just shared out things that we remembered from previous years about scientific notation. So let's review. We remembered that our first number is a coefficient between 1 and 10. We achieve that by moving this decimal place to a different spot to make this number a number between 1 and 10. 3 and 26 hundredths is a number between 1 and 10. It is then multiplied by a base 10. The base 10 also has an exponent, which tells us which direction and how many times to move the decimal. So in this example, our coefficient 3 and 26 hundredths has a decimal place here. And we're going to move it 5 times to the right because 5 is positive. 1, 2, 3, 4, 5. Our decimal would land here. In these empty spaces, we would add zeros as placeholders. Our solution would be below. 326,000 would be our final solution. Let's practice our knowledge of scientific notation converted to standard form on two very different problems. This first problem has a coefficient 7 and 78 hundredths. This in fact is a number between 1 and 10. Being multiplied by a base 10 and an exponent of positive 4. So what I do is write my coefficient and be ready to move my decimal 4 times to the right. 1, 2, 3, 4. My decimal would land here and I would add 0 in these spaces as placeholders. My final solution would be 77,800. Now let's look at the next example that is very different. Although it does have the same coefficient, 7 and 78 thousandths, being multiplied by a base 10, but this time the exponent is negative 4. When we write down our coefficient, and we know the exponent negative 4 tells us that our decimal place is going to be moved 4 times this time to the left. 1, 2, 3, 4. Our decimal will end here, and we would add 3 zeros as placeholders. Our final solution would be 778 millionths. You see that although these two problems look very different, the exponents make the solution very different. This used to be where we ended, but now that we're moving to our Common Core thinking, the solution is not all we need. We need to explain why. Why did all we have to do was move those decimals? What power does this base 10 have? What does the exponent mean to the solution? Let's explain that in two very different problems. We know that scientific notation makes it very easy to express very large numbers. In this first example, we're expressing the distance between the Earth to the Moon. The distance between the Earth and the Moon is a very large number, and it is expressed in scientific notation below. 3 and 844 thousandths being multiplied by a base 10 and an exponent 5. Before we knew that this exponent 5 told us to move the decimal 5 times to the right. But why? Our key goes into this base 10 with exponent. What do we know about that base? We know in expanded form, 10 to the 5th power means 10 multiplied by itself 5 times. So 10 times 10 times 10 times 10 times 10. When we multiply that together, we get 100,000. If we bring down our beginning coefficient, 3 and 844,000, and multiply that by 100,000, we get our final solution. The moon is 384,400 kilometers away. So we just proved that we moved the decimal 5 times by showing our exponent in expanded form. So this becomes simply one multiplication problem. Let's double check that we proved it correctly. Our decimal started here between the 8 and the 3. If we moved it 5 times, we should have gotten our correct answer. 1, 2, 3, 4, 5. Yes, we correctly proved the distance between the Earth and the Moon is 384,400 kilometers away. We also know that scientific notation makes it very easy to express very small numbers. In this example, we're expressing the width of a plant cell, which you could imagine is very small. We would have to zoom into the plant and look at its cells. The plant cell is right here expressed in scientific notation. 1 and 276 thousands. 1 and 276 thousandths being multiplied by a base 10 with a negative exponent 5. To prove this expression, we have to unpack what we know about 10 to the negative 5th power. In our last unit, we worked with a lot of exponents and positive and negative values. So what is an equivalent to 10 to the negative 5th power? Would it help you if I reminded you that 10 to the negative 5th power has a 1 underneath it? How could we express this positively? If we remember our last unit, we remember that negative exponents can be expressed positively if we flip our fraction. So the equivalent to 10 to the negative 5th power is 1 over 10 to the positive 5th power. How can we use this equivalent to help us prove the width of a plant cell? Let's return to our problem. So we just went over an equivalent to 10 to the negative 5th power is 1 over 10 to the positive 5th power. Below here, I expressed that in expanded form. So an equivalent is 1 over 10 times 1 over 10 5 times. So what I'm going to do now is multiply these fractions together. I get 1 over 100,000. I'm now going to bring back my beginning coefficient. I can look at this problem in a few different ways. I could look at it as a decimal being multiplied by a fraction, or for me personally, I like to look at it as a fraction being multiplied by a fraction. I know when I multiply fractions, what I do is I multiply straight across. So this will equal this fraction right here. I know fractions are secret division problems. So to solve this in my calculator, I would divide these two numbers. And we'll get the following solution. My solution right here is the approximate width of a plant cell. If our proof was correct, we would have moved our decimal 5 times to the left. So it originally started here between the 1 and the 2. Let's double check. 1, 2, 3, 4, 5. We are correct. We did a proper proof to prove going from scientific notation to standard form, that all we had to do was move our decimal an appropriate amount of times in the correct direction. Use these proofs to prove other examples of going from scientific notation to standard form.